With all of these factors that govern the rate of the reaction, which is how fast a reaction happens, we can take a closer look at one of these factors, and that's the concentration part. You see, the structure of the reacting species is fixed. We cannot change that. If the reactant is A and B, two reactants A and B, whatever they are, they are. We cannot modify that. And so we cannot modify the shape or orientation in which the reaction happens. What we can modify is the concentration of the reactants. And as we just learned, if the concentration goes up, the rate of the reaction increases. We can actually state that through an equation known as the rate equation, which we will see in a second. However, if we just make sure with the remaining three factors, then see if they too apply in the rate equation. The temperature of the reactants is also under our control. So if we were to increase the temperature, the rate of the reaction would increase as well. And it turns out that we can actually modify the temperature, and within the rate equation we will see we will also take the temperature into account as well. Now the physical state of the reactants, while we do control it, we only have a few choices, and many times a reaction may only happen in those states, so in that sense we do not really control it. And using a catalyst is applicable for some reactions but not others, so we are going to avoid talking about that as well. So concentration of the reactants as well as the temperature of the reactants is something we modify very frequently, and an equation built on that known as the rate equation is given to us here. What we have here is the rate equation, or a form of the rate equation, that allows us to see how concentration and temperature affect the rate. Basically, here is the reaction where dinitrogen pentoxide, 2 moles of it, decomposes to produce 4 moles of nitrogen dioxide gas and 1 mole of oxygen gas according to the balanced equation. This decomposition happens by supplying energy in the form of heat, and that's when the reaction happens. Since the concentration of the reactant modifies the rate of the reaction, we can say that the rate is proportional to the concentration of the reactant. The square parentheses here, or the square brackets, mean concentration, and this sideways half 8 looking symbol means proportional, or it's a symbol for proportionality. The rate is proportional to the concentration of the reactant, which is the only reactant we have here. Now the rate equation only involves the concentration of reactants, one or more, not the products. And the reaction may have many steps involved in it, but whether there are many steps or just a single step, it's only the reactant or reactants which show up in the rate equation. For this rate equation, we say that as the concentration of dinitrogen pentoxide increases, the rate increases. Hence, it's directly proportional. The rate is directly proportional to the concentration of dinitrogen pentoxide. But if we want to use the equal to sign and actually say rate equals the concentration of the reactant, there is a certain constant called the rate constant which must be introduced. And so the equation becomes rate equals K, lowercase k, rate constant, times the concentration of dinitrogen pentoxide. Now I said earlier that within the rate equation we will have the concentration term, one of the factors that can modify the rate of the reaction, which you can see here, but also the temperature. Well, the temperature's effect is taken into account in the rate constant. So when the temperature goes up, the value of the rate constant will change. We report the rates at particular temperatures for a particular rate constant. If the temperature changes, the rate constant will change. So as this reaction involves the decomposition of 2 moles of dinitrogen pentoxide to produce 4 moles of nitrogen oxide, nitrogen dioxide and oxygen gas, there are a few other questions to ask. What about the fact that 2 moles of dinitrogen pentoxide are involved? Do we take that into account? It turns out that the coefficients do not show up or do not necessarily show up on the rate equation. In this case, it does not show up at all. However, the rate equation does have an exponent term when it's written in a very generic form given here, where a reactant is forming products. In the exact example we use here, the value of that superscript here is 1, and so that value has nothing to do with the coefficient in the balanced equation. How exactly do we find out the value of n, which is the exponent? N is known as the order of the reaction in this case. Well, it is only determined experimentally. You cannot just figure it out by looking at the balanced equation or doing some math. Experiments that we are not going to go deep into in our course enable chemists to find out the value of the rate constant. I mean the order of the reaction. Now, if the value of n equals to 1, we say it's first order. If the value of n equals to 2, we say it's second order. So this is the generic form of a rate equation. But if you have more than one reactant, it's likely that the other reactant also shows up in the rate equation. It's not necessary for it to show up, but it may show up. Now, when might it not show up? Let's say I write down the rate law, the rate equation with rate constant times the concentration of one of the reactants with the order with respect to that reactant, whatever the value of n is, and then B with order with exponent which tells you the order of the reaction with respect to that reactant. But if the value of this n prime is equal to 0, then B raised to 0 equals to 1, and hence it gets eliminated from the rate equation completely. That may or may not happen, and that's why in this case we are writing down the generic version where rate equals to the rate constant K times the concentration of reactant A raised to n times the concentration of reactant B raised to n prime. Here is an example: methane plus oxygen gas reacting to produce carbon dioxide and water, the balanced equation. And it turns out that the rate of this reaction depends on both of the reactants, and it's K times methane concentration times n, superscript n, times the concentration of O2 times superscript n prime. So again, the values of n and n prime have to be determined experimentally, and for the reaction that involves the oxidation of ethanol, for example, which is not shown here, but in the oxidation of ethanol, ethanol combines with oxygen gas to produce a product. In that case, both of the reactants, ethanol and oxygen, are involved in the rate equation, and it turns out that this is the actual form of the rate equation, where the value of n here is equal to 1, and it's eliminated because by default we do not show 1. It's understood to be so, it's not written, while the value of the exponent over oxygen concentration is 3. So we can say that this rate is first order with respect to ethanol and third order with respect to oxygen. First order with respect to ethanol and third order with respect to oxygen. What is the overall order of this reaction? The overall order is the sum of 1 coming from the value here not shown and 3, which is 4. So we can say that the overall order of the reaction is fourth order. We will not go into how experimentally the values of these orders are determined, the exponents to the reactant concentrations, but How to interpret the rate equation is what we just discussed, and anything beyond that is beyond the scope of our course. So we will keep it simple and just interpret the rate equation and the order, the overall order of the reaction, as well as the order with respect to each of the reactants involved.